Continuing in our discussion of similarity. Last class, we talked about if you have two triangles, and you know that, for example, the sides here are A, B, and C, that the triangles are similar if there's some constant, some scale factor that you multiply times this to reach the length of its corresponding side over here. And you would multiply the other sides times that same effectively coefficient of dilation or scale factor. And if you multiply each of these values by k, then these results end up being AK and BK and CK. And what you notice then is that the ratio of any corresponding pair, AK over A reduces to K, and BK over B reduces to K, and CK over C reduces to K. In other words, the ratio of corresponding sides is consistent. And in fact, what's a little bit new, last time we talked about the fact that the perimeter is also going to have that same scale factor. But what I'm introducing today is the idea that even if you were to look at, for instance, the altitude, a specific line segment going through the shape that measures perpendicularly from one side to the vertex on the other side, that would also be in the same scale factor. They'll all be in the same ratio. Since they're in equivalent ratios, we call that all linear dimensions being proportional, because they're all in the same ratio. Any length measurement, the length of the sides, the length of the altitude, the length around the outside, the perimeter, anything that uses inches, meters, centimeters, something you'd measure with a ruler. However, if instead you're talking about areas like square inches or square meters or square centimeters, there's a little tweak to it, a little difference. So for example, we're looking at two squares here, and we know that these two shapes are similar because they both have the same angles, 90-degree angles, and I can find the ratio from this side to this side and this side to this side, and they're all consistent. So I'm going to do a little activity here just to show that that's true and what happens to the areas. So first we'll talk about the length ratio, as I like to call it, the LR. If we want to find the scale factor from figure 1 to figure 2, we're going to take a length of 1 and a length of the corresponding part of figure 2 and create a ratio from it. We can call that 2 to 3, or we can call it 2/3. If I then were to look at the perimeter, 2 plus 2 plus 2 plus 2 is 8. And 3 plus 3 is 6, plus 3 is 9, plus 3 is 12. But when I reduce that or simplify that, I'm going to get the same 2/3 as my scale factor. And even if I were to look at some other crazy dimension that's a length dimension, like a diagonal going straight across there and going straight across there. We'll soon work with this in more detail, but this is a right triangle. That gives us the ability to use the Pythagorean theorem. So 2 squared plus 2 squared equals this distance squared, which means 4 plus 4 equals this distance squared. So 8 equals this distance squared. So this distance is the square root of 8, which simplifies to 2√2. Similarly, this has the same scenario. 3 squared plus 3 squared equals this distance squared. 9 plus 9 equals this distance squared. So 18 equals this distance squared, so the square root of 18, which is 3√2. And if I take the scale factor or the ratio of these two figures, 2√2 over 3√2, I can cancel the root 2's, bringing me back to the same scale factor, 2 over 3 or 2 to 3. In other words, no matter what linear dimension I use, it gives me the same scale factor, 2 to 3. However, what happens with the areas? If I want to find the area of figure 1, it's a square. So that means I just need to do length times width. 2 times 2 is 4. And if I wanted the same with figure 2, it's going to be 3 times 3, which is 9. And that's going to give me a ratio of 4 to 9, or 4 over 9. Now, lot of us, when we look at 4/9 and we look at 2/3, we think that 4/9 can be reduced to 2/3. And that there's a relationship between them, and people make the mistake often thinking that it can be reduced, but I want to do a little extension understanding of why that's not true. So when I have something like, let's say 6/9, and I want to reduce that, what I'm really doing is I'm calling this 2 times 3 over 3 times 3. And effectively, I'm then separating this and saying that it's really 2/3 times 3/3. And we know that 3/3 is a version of 1. So since it's a version of 1, it doesn't change anything. In other words, this can cancel, leaving me just with 2/3. In other words, what I did to both top and bottom is I divided by 3. And I can divide top and bottom by the same number. I can multiply top and bottom by the same number, but I can't add top and bottom by the same number, right? I can't say 1/2, and then if I add 1 here and I add 1 here, that makes 2/3. Oh, that's the same as 1/2. We know you can't do that. So in the same way, I can't say that, for example, if I want to take 1/4 and reduce it, I can't take the square root of those because that would equal 1/2. And we know that 1/4 is not equal to 1/2. So 4/9, even though it kind of looks like 2/3, they're not equivalent fractions. In other words, the length ratio is not the same as the area ratio. It turns out that if the length ratio is A/B, the area ratio is A²/B². Every single time, because when you're multiplying 2 lengths to find an area, you're going to have that A multiplied twice. So this is what goes in the bottom here. The rule is if the length area is A to B or A/B, then the area ratio is A²/B² or A²/B². And we're going to do some practice problems to get you comfortable using that. Any questions so far? Okay. Page 2, we'll start with just if the perimeters of 2 similar polygons are in a ratio of 18:54, find the ratio of the corresponding sides. So they're giving us a ratio. And the question is, do we have to adjust it, or is that it? They told us this has to do with the perimeter. Is the perimeter something that is measured by a ruler? In other words, is it in inches or feet or miles or centimeters, something like that? Or is it measured by like how many squares or maybe how many Post-its can fit on top of it to cover it, right? That's a unit of area to say, if we put on 20 of these, it would cover it. That would be a description of area. Whereas if I were to say it takes 1, 2, 3, 4 inches to cover it, that's a measure of length. Well, perimeter and sides are both the same type of dimension. They're both length ratios. So I would say that the length ratio is equal to 18/54. And then because I recognize that those can be reduced, I would go through the process of reducing them. Okay, that's got a 9 in it, that's got a 9, so that's 3/6. It's still got a 3 in them, so oh yeah, 18 goes into 54. It's 1/3. That's the reduced scale factor for the ratio of sides. But now, when it says find the ratio of the corresponding areas, that's something different. And so to find what I call the AR, the area ratio, we're going to have to take this ratio, 1/3, and square both top and bottom. In this case, that gets a value of 1/9. And that's going to be the ratio of their areas. How does that apply or help us? Well, let's do problem number 2 here. 2 triangles are similar. Smallest side, smallest side. So we've got a pair of numbers that match. This is a side, and this is a side. So what I'm going to do is I'm going to start off by saying LR equals and AR equals. And the problem has to give me a ratio, either LR or AR. In this case, because they gave me two corresponding side values, I'm going to make those my ratio, 12 and 36. And just for ease, I'll reduce it. Instead of just 12 over 36, which are big numbers to have to square, it would be more convenient for me to hold on for a second. I'm checking the chat. There's some stuff going on here. The notes are, as always, in Canvas. Are you guys seeing my screen frozen?
No.
Huh. Looks like 2 or 3 people did. Emily, are you back? Grace, you back?
For me, it's still frozen.
Grace is still frozen. Okay. Emily, how about you?
It's still frozen for me too.
Really? So when I move that screen, you're not seeing it move, huh? But some of you are. Who's seeing me like jiggle my paper right now? Give me a thumbs up. Okay. All right. So I'm sorry to say that it's probably one of your neighborhoods, right? Like you guys may live in the same internet neighborhood and you're probably getting locked down somehow. But I am recording this session, so you'll be able to play this session later. And I believe that that should be recording this particular image. If not, I'll do it again. Okay, so back to this. My LR is 12 over 36 because those are the numbers given to me. I'm going to reduce it because it's easier to work with. So 12 goes into 36. Again, it's 1 over 3. Once I get my length area, always, 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 I just square the top and square the bottom to get the area ratio, 1 over 9. And then I look at what the problem's asking, because it's always either going to say something like, if the perimeter of the large is 27, what's the perimeter of the small? Or if the altitude of the large is this, what's the altitude of the small? Or if the area of this is that, what's that? And you're going to use either the LR or the AR. In this case, notice what they say. If the area is 100, what's the area of the second one? So which ratio are they asking us to use? LR or AR?
AR.
Yeah, they're asking us to use the AR. So what I'm going to do is I'm going to use the AR. I'm just going to say 1 over 9 equals. I've got my ratio, and I'm going to make a proportion, which is an equation of two ratios. And the other number they gave us is 100 centimeters squared. So that's going to go in either the top or the bottom. And it depends upon the circumstance and the way it's phrased to decide whether it goes on top or the bottom. Initially, it said the smallest side is 12. Excuse me, first triangle is 12 and the second triangle is 36. So I put first triangle over second triangle. That's the way I set it up. So that means the first triangle is supposed to be on top because that's where I put the 1. So we expect this 100, which is part of the first triangle, to align or match with the first triangle information I already put in. It's asking about the second triangle, which came from the 36. So that would be lined up here. So that's where I put an X. This particular problem is probably intuitively solved by you. You see that 1 times 100 makes 100, and 9 times 100 should make this 900. But the process is to cross multiply and solve. So I take 1 times X equals 9 times 100. There's nothing to divide by, or you can divide by 1, and you get that X is equal to 900 centimeters squared. That would be the area of the second triangle. Are we still frozen for some people? Those of you that had a frozen screen before, is it still frozen? Please give me a thumbs up. Still frozen, okay. Bummer, looks like there's about 4 of you. And some of you are getting really slow responses. I don't think that's anything I'm doing, but that's a lot of you. Okay, I want to skip number 3 for a moment. We'll come back to that later. Let's go to number 4. 2 polygons are similar. The altitude of the first is 24, and the altitude of the second is 16. So that's our pair that they gave us. Altitude of 24 and altitude of 16. Always, 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 I set up my LR and my AR. And when they're talking about altitude, are they telling us length or an area measurement?
Length.
Length, good. So I'm going to say 24 over 16. And I could leave it like that and just square it directly, but let's make life easier on ourselves. Let's reduce this. So 24 and 16 both have an 8 in them, so I can change it to 3 over 2. That's my length ratio, which means my area ratio is going to be 3 squared over 2 squared, which is 9 over 4. Now we'll look at the problem that's being posed. If the area of the first is 270, what's the area of the second? So they're asking us about the area ratio. So I start with 9/4 because that's my area ratio. And then I create my proportion. It says the area of the first is 270. Well, my first was 24, which was my top. So I need to keep it in line with that. My 270 is on top because that's my first. And I'm looking for the area of the second. That's going to be on the bottom. And again, you may be able to just see how this changes. 90 times 30, or 9 times 30 makes 270. So 4 times 30 is 120, but let's do the process. Cross multiply. 9 times x equals 4 times 270. Divide by 9, divide by 9. X equals, that would actually simplify to 30. 4 times 30 is 120. And this is meters squared. Okay. So now, let's change it a little bit. Starts the same way, right? We get 2 similar polygons, but this time it tells us that their areas are in a ratio of 36 to 49. So if I start off with my LR and my AR, is this going to be an AR or an LR to start with this time?
AR.
This one's an AR. This is our area ratio of 36 to 49. And previously we would just take our length ratio and square it to get the area ratio. But now we're starting with the area ratio. So how are we going to go back to get the length ratio?
Square root.
Excellent. So we'll just take the square root of these. And we have the option of reducing them first if they do reduce. In this case, they don't. And that gives us a length ratio of 6/7. And this time it's not asking us any more than just to identify that. Find the ratio of the corresponding sides. Okay, would you guys try number 6, please? Do that yourselves. I've sent a question to those that are having the freezing problems. If you please respond directly. Wow. It's weird. You guys are in very different neighborhoods. I thought maybe it was all in the same neighborhood. 2 of you in Tam Valley, 1 in Strawberry, 1 in Homestead Valley. Okay, so this one we start off with LR and AR. This time they're giving us areas again. So I'm going to start off down here, which means my length ratio is going to be the square root of those, which is 11 over 10. So the ratio of the corresponding sides is 11 to 10. Okay, how would we use this to solve a problem though? Well, the area of two similar figures is 136. If the perimeter of the smaller one is 30, what's the perimeter of the larger one? So again, we'll start off with our LR and our AR. This time they give us areas, so I'm going to put those in the AR. And this time there's a chance to reduce them. I could reduce these because they're both even numbers, for example. But I'm not going to because I see these are perfect squares. 100 is 10 squared and 36 is 6 squared. But of course, that means that now I can reduce the result. So my length ratio can reduce. It's got a 2 in both of those. So I'm going to say 5/3. Now I'll look at the problem. If the perimeter of the smaller one is 30, perimeter, okay, if when I measure perimeter, I'm using a ruler to figure out how long it is. That means I'm going to use my length ratio. So I'll say 5/3 equals something. And I need to figure out whether that 30 belongs on top or on the bottom. It didn't really tell me much about the two figures, but here it says the perimeter of the smaller one is 30. Well, if I put this number on top, because I'm setting it equal to a fraction greater than 1, the denominator will end up smaller, so it won't be the smaller one. But 3 is smaller than 5, so 30 should be smaller than x. And again, I've set these up to be not surprising, but let's do the process. 3 times x equals 5 times 30, divide by 3, x equals 50 meters. Can you please give me some feedback? How do you feel about solving problems with LR and AR? 5, this seems really easy and straightforward. I can do this every time. 3, I'd like a couple of example problems myself to see how I do with it, but I think I can handle this. 1, something is confusing me in this process. I'm going to need to get some clarification. Okay, pretty good scores. So the one last one that I haven't shown you is a little bit of a twist. It's actually pulling in some stuff from last class as well as this one. It starts off okay. The perimeter of two similar triangles is in the ratio of 2 to 4. Okay, LR, AR. We know that this is a perimeter, so that's a length ratio, 2 to 4. I'm going to reduce that to 1 to 2. And we want to talk about their areas. So let's get our area ratio. I'll take my 1 over 2 and I'll square them both, getting 1 over 4. But then it's not asking us to solve a single area. It doesn't give us the area of a single one. It tells us that their sum is 100. Remember the extended ratios we did last class? So if we know that the two parts are 1 and 4, the two parts, when weighted, have to add up to the whole. So when I multiply them by some value, x, they'll have to add up to 100, which allows us to say 5x equals 100, x is equal to 20, which means that my two triangles are 1 times 20 equals 20 centimeters squared, and 4 times 20 equals 80 centimeters squared. Those are my two triangles. Any questions on using length and area in similar figures to solve problems? Somebody asked how I got the 1x and the 4x. This came from last class where we talked about extended ratios, where the parts of the weight, the sum of the weighted parts equals the whole. So since they're asking for the sum, and I've got ratios, I'm going to say 1x plus 4x equals 100. And that way it could be 1 and 4, could be 2 and 8, could be 3 and 12, could be 4 and 16, could be 5 and 20. Turns out it's 20 and 80. Okay. Before we move on to the last piece, which is this one, I want to give a little refresher for what we did when we did congruent triangles. Remember I showed you the video with the Mario Kart, and we talked about finding congruent triangles by looking at three components that were A's or S's. And some of them proved congruence and some of them didn't. Oh, that's all fuzzy. Well, conceptually, if I've got three slots to fill and I'm filling with A's or S's, I could have all three A's. I could have one S, which could appear in any of three locations. I could have two S's appearing in a variety of locations. Or I could have all three S's. That's the world of possibilities. There's nothing else that could happen with three spaces and A's and S's. And what we discovered last time when we did congruent triangles is that some of these things were great for proving triangles are congruent, right? In other words, if we had side, 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 that was enough information to demonstrate that the triangles we're talking about must be identical. If we had side, angle, side, they had to be identical. If we had angle, angle, side, they were identical. And if we had angle, side, angle, they were identical. And some of these things were bad, right? Like this one proves the ambiguous case. We don't want that one, so we cross that out. And we recognize that this one is really the same as that one, it's just backwards, so we just choose not to use that one. Similarly, this one is the same as that one, so it's redundant, so we're not going to use that one. Why didn't we use angle, angle, angle? In other words, why won't two triangles be congruent if you know that all the angles are the same? Well, I could have one triangle with angles of 30, 60, and 90. And I could have another triangle with 30, 60, 90, right? The angles are the same, but it's a much bigger version. And that meant that we couldn't prove the triangles were congruent, but it will allow us to prove the triangles are similar, because if you expand the triangle, keeping the angles the same, even if the sides get stretched out in the same way, like a dilation, the triangles will stay the same shape. They're just different sized versions. Which means having all three angles is enough to prove triangles are similar, but we can be even smarter than that. Do you remember when we did the triangle angle sum theorem and we came up with some corollaries? One of the corollaries was if two angles in one triangle are congruent to two angles in the other triangle, then the third angles must be congruent. So we don't actually need all three of these angles. We just need two of them. And if two angles by themselves will prove triangles are similar, then is there any new information in us using AAS? Because it's got two angles in it. And angle side angle also has two angles in it. So we don't need new theorems for those. For triangle similarity, there are only three theorems we're going to use. Angle, angle, side, and side, side, side. Today, we're going to just broach that subject, just get you started working with angle, angle similarity. What angle, angle similarity says is that if I've got two triangles, each with a pair of angles that line up, that are congruent, then those triangles must be similar. So in this case, in problem number 1, I've got my two triangles here. I don't see any angles marked. How can I know if any of the angles are congruent? Well, we might remember that angle DEC and angle FEG make up a certain pair of angles. What kind of angles are those?
Vertical.
Very good. Vertical angles, and we learned that vertical angles are congruent. We also see we've got these arrows on here. What do those arrows mean on these lines?
Parallel.
Good, means they're parallel. And here's a transversal, which means that if parallel lines cut by a transversal form some angles, that those could be congruent. So we could end up with these angles, for instance, being alternate interior angles. That's being enough information with the vertical angles and the alternate interiors to say that yes, they are similar by angle-angle similarity. And because of that, we can then write a triangle similarity statement. Just like we did with congruence, but this time we use a similarity symbol between them. So I'm going to name the left triangle similar to the right triangle. When I name this left triangle, I've got a lot of freedom. I can name it those three letters in any order I want. Let's have someone who hasn't talked today or this week or last week. Be bold and name this triangle for me. If you use all three letters, you can't be wrong. There we go. Someone wrote it for me. EDC. Someone else said CDE, and they're both right. It doesn't matter what you pick this first time. I'm going to choose CDE. This first one is a totally free guess. It doesn't matter what choice you make, as long as it's those three letters from the first triangle. But now that we move over to this other one, we have to match them up. So I've got C that has no marks on it congruent, D that has the two greens, and E that has the one purple. If C is first, then I have to choose G because that's the same. D is second, so I have to choose F because that's the same. And then E is the same for both of them. This is my triangle similarity statement. Any questions? Okay, how about number 2? Do you see the two triangles? First one's pretty evident. Second one sometimes eludes people. Now, do you see that there's two pairs of angles that are congruent? Can anybody help me find them?
Angle LQP is congruent to QMN by corresponding.
Very good. We got parallel lines, so those two angles are corresponding and thus congruent. We could use the exact same logic to say that these two are also corresponding, or we could say that L is reflexive. It's shared by both of them. Either way, we can say yes, similar by angle-angle similarity. Therefore, we get to create the triangle similarity statement. Ellery, since that was your poll, why don't you name the first triangle for us?
Triangle LQP.
Sounds great. Is that the only answer that's right? Not at all. You could have even chosen the big one first. It doesn't matter. But once she's picked the first one, the second one's locked into place. Can I get a different person to please match her triangle? What do I have to call this one? So LQP matches to what? Okay, close. Somebody sent me PMN. P isn't the tip of the triangle, right? So LMN is what we want to see there. LMN, good. Okay, we want to make sure that all the pieces line up. Somebody else sent me a different answer that wasn't quite right. So if we want Q to be the second letter here, that's the one with one mark. So we want M, the one with one mark, to be the second letter. And if we've got P with two marks to be the third letter here, then N needs to be the third letter. And then L is also congruent. Okay, what about number 3? Do we have two angles that are congruent here?
One angle is 90 degrees, so those are congruent.
One angle is 90 degrees.
Or two, I mean, one from each triangle.
Right, but we've got to have two from each triangle. So we're halfway there. You're right. That 90-degree angle is really important. That gives us one piece of information, but we need one more piece of information. And certainly the information they're giving us looks not right, right? 39 and 51, I can tell you those are not the same number. But there's three angles in a triangle, aren't there? So if we know that this angle S and 39 and 90 make 180, S plus 129 equals 180, then S must be 51 degrees. And once I do that, can we see then that we actually do have similar triangles because those angles are also the same. So we can say yes by AA similarity. And that lets us then say that triangle, and Alexis, how about you? Why don't you name our first triangle for us here?
SEY?
Sounds great. And can I get somebody to match the triangle that must go with it? This one's harder. Let's get somebody new who's hiding in the wings and brilliant, at least at this skill. Okay, somebody just texted into me, catching, actually two people did with the same answer. So you saw that 51 matches with W, so that's correct. But don't just jump to the conclusion. Then we went to E, which is the one that's not a right angle. So WHC. Very good. Great. Several people got it right. Nice. Okay, what about 4? Let's try the same trick. We got one. We got the 68. That's easy. let's find E and see if it's the right size angle. So E plus 68 plus 63 equals 180. So E plus 131 equals 180. So E equals 59. Oh, 49, excuse me, 49. That's not the same as 54. So no, not similar. These two triangles have different angles, therefore they can't be similar. All right, would you please do 5 and 6 yourselves? Determine if they're similar. If they are, write that they're similar, as well as the similarity statement. Okay, how about number 6? Somebody finish us off here. This is actually the last one we're doing today. Probably someone who's not frozen. It's so painful to wait.
I can do this one too.
Okay, thanks, Emerson. What do you got?
Okay, so I said that they were similar by angle similarity because they already gave you the one angle that was similar, P and
Right.
Z, and then I kind of forget what it's called, but the line going straight across for both, like P, X, Z. I said that the two angles there were congruent.
Good. These two angles here, right?
Yeah,
They are, because they're vertical angles.
yeah.
Yeah, I mean, we haven't used that word in a while, but exactly, we need to know that. So they're vertical angles. And as a result, we get to say that the triangles are similar. So I'm assuming you're going to be on the hook. What's the first triangle? This part's so hard. What do you get? You can pick any of these 3 letters or any of these 3 letters in any order.
PQX.
PQX sounds great. PQX. But now that that's been done, someone's got to fix it and figure out what the matching piece is. Who's got it for me? See him coming in. ZYX, very good. Coming in the text. All right. So let's see how we're doing here. How do you feel about angle similarity? Can you identify if they're similar? And if so, state the similarity statements. 5, yes, I can. 3, I've got some skills, but I want to practice a little more. 1, this eludes me. Good, good scores. All right. Based on the time we've got left, I'm going to table the rest of this page for our next class. So we're not going to finish the rest of these notes. You're not responsible for finishing them. I don't want you to finish them. I don't want you to ask more. Instead, we're just going to stop at this point. Your homework is in Big Ideas Math, and it covers the LR and AR stuff we did, as well as this angle similarity. And then on Thursday, we'll do chapter 8.3, which is SSS and SAS. If you're interested in hanging out because you want to be in a breakout room and be able to ask questions, you are welcome to. Otherwise, I am happy for you to go offline and do the Big Ideas Math yourself at your own leisure. Those of you leaving, have a good day. Those of you staying, you're welcome to stay.
Thank you.
Thank you.
Sincere, do you need some help? Johnny, do you need help? Johnny, do you need help? Johnny, you there? Sincere, you there?
I'm sorry, I just had to go use the bathroom. I'm sorry, Mr. Erlin.
Okay. I dismissed people to go work on the big ideas work. You can go to big ideas and get that done yourself, okay?
Okay, Mr. Erlin. Thank you.
You're welcome, thank you. And then there was one. Johnny, you there? Let's kick him off.
Hey, Chris.
Hi. So I did the same for all my classes, even though I created this worksheet that had SSS and SAS. I learned in first period, there just really wasn't enough time to get through that.
Okay.
And that's okay. That's actually still in line with our schedule. I just thought I'd be able to push through more and I didn't want to. So
Okay.
I think that's consistent. How'd that
Okay.
go for you?
So that's what I'll do tomorrow.
Yep.
Okay. Okay. And then you'll post the video somewhere,
Yep.
right? Or send it to me or something.
Yep.
Because I love looking over it, again and
Sure. As soon as we finish this, oops, I'm recording it right now.